All right, let's get, oh, that's loud. Okay, let's get started. Good morning. Okay, try that again. Good morning. Good. So the reminder for the exam next Thursday, October 19, 6:30, 7:30 to 7:30 p.m. Same place as last time. The seating arrangement is exactly the same. So just go where you were last time. Okay. Now on the other projector here, I'm participating in this professor dress-up thing here. Every day there will be a Relay for Life little pouch here. So any donation you want to put in there for Relay for Life, there's a goal. Once we reach that goal, I'm supposed to dress up as a superhero for the class closest to Halloween. So, if you have some change you want to give to Relay for Life, it's a great cause. So think about it, okay? I don't know we'll meet that goal first and then we'll decide what superhero we're thinking of. Okay? All right, so today we're going to be looking at the first part of section 3.9. The topic is on related rates. This section is not on exam 2. Exam 2 will end on what we did last time. So what we're doing today and what we're doing next Monday will not be included on the exam. Okay, so related rates here, there's really nothing new. All we're going to be doing are going to be looking at applications using the chain rule. And oftentimes implicit differentiation. There really is nothing new here. Everything you need to know, you already have seen. All right, so just like last time, I've typed out a few examples to save us some time from writing them down. Here's the first one. And I don't know why there's a green line on that screen. I can't make it go away, so just look around it. Okay, in the first example here, we have a bug crawling on a circular track. And this circular track can be described by the equation x squared plus y squared is equal to 225. That's a circle centered at the origin, radius square root of 225. So this thing is going around on that track. At the specific point, 12, 9, when x is 12, y is equal to 9, it has a certain velocity. And the vertical component is 4. We want to find out what is the horizontal component of the velocity at that point. Okay, let me put this on the other projector and now work on this page. All right, so let me sketch a picture here so you can get a better feel of what's going on. This bug is crawling on a circular track. Centered on the origin, and the radius is square root of 225. And so this little guy is crawling around on this track, let's say going counterclockwise. And now at this specific point here, let's say this point is 12, 9. That is the direction of this bug's velocity. Velocity is tangent to your path, right? So that's the direction that this guy is going. You can think of that green arrow as made up of two other arrows, one pointing upward and one pointing to the left. So those two combined gives you that green one. The problem told us that at this point, 12, 9, the vertical velocity, and that would be this one right here. So that vertical component of the velocity is 4. We want to find out what is the horizontal velocity. Okay, does that make sense what's going on here? Yeah? Okay. If the vertical velocity is 4, that means it's the rate of change of the y component of his position. Rate of change of y component. Of where that bug is. And of course, we have a symbol for that. It's the rate of change of y, so dy dt, right? As time goes on, this thing is, at this point right here, dy dt is going at the rate of 4. And we know it's positive 4 because it's going upward. And our goal here is to find out what dx dt is equal to. We're trying to relate these two quantities. How is dy dt related to dx dt? And that's why these problems are called related rates. You know the rate of something, and you're trying to relate it to something else. We know dy dt. We would like to relate it to dx dt. Okay. We also know how x and y are related. Because we know the equation of that circular track. Anywhere on that circular track, whatever x component the position is, it's got to be related to y by this equation. If you know one of these two, you know the other two automatically. They're always related by this equation. So if we go ahead and take the derivative of this, we should be able to somehow relate those two quantities. Because the bug is walking around this entire time. X and y are implicit functions of t, of time, right? They're both implicit functions of time. So we're going to take the derivative of this equation here with respect to time. On the left side, we get derivative of x squared with respect to t, derivative of y squared with respect to t, and right-hand side, the derivative of 225 with respect to t. And that's just the usual implicit differentiation we have been doing. It's a little bit beyond what we have been doing in the past in the sense that we now know that these two things are both related to a third variable, t. When we take the derivative, be careful to use, got to use the chain rule here. X is a function of t, right? So when you take the derivative of that, we get 2x times dx dt by the chain rule. Same thing here. Y is really a function of time. When you take the derivative, you get 2y. And now you got to account for the fact that y is something more than just t. Y is something to do with t. We don't know exactly what it is, but we know it contains a t. Therefore, the chain rule has to apply. Okay, right-hand side 0, of course. It's a constant. Now look at the other slide here. We know one of these two things. We don't know the other. We want to know dx dt. Subtract that over and divide it by 2x. We get negative y over x times dy dt. Okay, so this is saying that at any given time, the vertical component, the horizontal component of velocity is always equal to negative of the y component of position divided by the x component of the position times the vertical component of the velocity. This equation holds for all instances of time. The only trouble is when x is equal to 0. But we're not dealing with x is equal to 0, so that's not a problem here. At the specified location, 12, 9, this is x, of course. This is y. The problem told us dy dt is equal to 4. So finding dx dt is very easy, plugging everything you know into that equation. Negative 9 over 12 times 4. So that's going to give us a, 3. Negative 3, sorry. Okay, just like with y, if y's velocity is positive, it's going up. If it's negative, it's going down. With x, if it's positive, it's going to the right. If it's negative, it's going to the left. And if you look at the picture from the last page, it makes sense. At that particular location, if he's going counterclockwise, the vertical component is up and the horizontal is going left, right? Otherwise, he would not be going counterclockwise. One very, very important thing to note here is you can only plug in numbers after a derivative. So this x is equal to 12, y is equal to 9, and dy dt is equal to 4. None of these is going to impact anything you do until you've taken a derivative and gotten what you wanted in this step. If you plug in these before you got here, your answer will be wrong. And this is a common thing with all of these problems here. If you have given specific numbers, only deal with them after the derivative has been taken. Okay, does that make sense? Any question on this example? Good? Okay, ready for the next one? This next one is a little bit more complicated, but that's okay. It's actually quite interesting. In this example, we have a street light mounted at the top of a 5-meter pole. A man that's 2 meters tall walks toward the pole with a speed of 3 meters per second. How fast is the length of his shadow changing when he's 15 meters from the pole? And also want to find out how fast is the tip of his shadow moving at that same instant in time. Let me sketch a picture here. It'll make it more clear. Street light, 5-meter tall pole. So here's the light. And this is 5 meters tall. And then you got this guy here that's 2 meters tall. So right here, this guy, 2 meters tall. And this is ground, of course. Okay, and he's walking toward the light here. If you think about what, imagine yourself walking toward the light in a parking lot or something. If you're walking toward the light, your shadow is behind you, right? Because what is shadow? Shadow is the fact that light cannot get past you. So if you draw a line from the light past the tip of his head, then this portion right here, this will represent his shadow. Right? That's what shadow is. Light cannot get past something. Look at my hand here. Light cannot get past it, so there's a shadow. Shadow is behind this guy. And depending on where he is, the length of the shadow is going to change. And he is changing his position all the time. He's walking towards the light at this particular speed, 3 meters per second. We like to know, as he's walking around, what is the length of the shadow doing? We know it's going to be lengthening or shortening, we'll find out, but at what rate? And also, if you look at the tip of this shadow, what is it doing? How fast is it moving? Okay, does the setup here make sense? Okay. Okay, let me ask again. Does it make sense? Okay, good. Let me redraw this picture here. I'll remove all the excess things like the guy and the light, and then we'll just work with the triangle. The left part of the triangle here represents the light pole, 5 units long, 5 meters. All the units are the same here, so we can drop the units without losing any information. So that's 5. And this one here represents that guy, 2 meters tall. I'm going to label the distance from the man to the light pole as x. And I'm going to label the length of his shadow that he's dragging behind him as y. Okay? Okay, so the problem says that he is walking toward the light at 3 meters per second. Mathematically, how would you express that sentence right there? Walking toward the light at 3 meters per second. How would you express that? One very simple equation. dx dt is 3. Is the distance between him and the light getting bigger or smaller? Smaller. So what should the rate be? Negative. Good. So the rate of change of the distance, dx dt, with respect to time. As time goes on, the rate of change of the distance from him to the light is shrinking. He's moving toward the light. So x is getting smaller. So a negative rate of change, and he's walking at 3 meters per second. Negative because x is getting smaller. Okay? Now we want to know how fast the length of his shadow changing. At the instant when he is 15 meters, from the pole. Okay, the same equation here in mathematics. What quantity are we looking for? Okay, back up. One step at a time, one step at a time. Answer my question first. What quantity are we looking for? Express this in mathematics. How fast is the shadow? Yeah, okay, so what quantity is that? dy dt, right? Yeah. So we want dy dt when 15 meters from the pole, that's x, right? When x is equal to 15. Okay, so we know the rate of change of his distance from the light. We would like to relate that rate to the rate of change of the length of his shadow. Once again, the common thing of these related rates here, you know the rate of something, you're trying to relate it to something else. We know that. We'd like to know how that is affected by this. We know it's going to be affected by it. Where you are from the light, that's going to determine how long the shadow is. So if you're changing distance from yourself to the light at any time, the shadow behind you will be changing length. right, so now we got to relate x and y. I'll redraw the picture here. So, who has an idea how we can relate these two variables? I know you do, but I want to hear from somebody else. Who has an idea how to relate these two variables? Right. Very good. Excellent. If you look at these two triangles here, the big triangle with a height of 5 and base of x plus y, and the smaller one with a height of 2 and a base of y, are what's called similar triangles. Who has heard of that term before? Okay, now for those of you if you have never heard that before, if two triangles are similar, that means they share angles. If you look at this angle right here, they share this angle right here, right? This angle is that. That also is the same angle in the smaller triangle. So these two are called similar. If they are similar, then the ratio of their sides will always be equal. The ratio of the height to the base of the big triangle, 5 over x plus y, is going to be the same as the ratio between 2 and 2 over y. And the reason is because this ratio right here represents the tangent of this angle. If they're the same angle, that they have the same tangent of that angle. Tangent is opposite over adjacent, right? So tangent of this angle of the big triangle is this guy, which also is the same as the tangent of the smaller triangle. And that's this thing right here. So that relates the two variables x and y by this equation. Let's rewrite this one here. Cross multiply. Simplify a little bit. And finally, if I divide it by 3, I get y is equal to 2 over 3 times x. Okay, and that's precisely how these two variables are related. The distance from him to the light, x, and his length, the length of his shadow, is always related this way. The shadow is always two-thirds of how far he is from the light. If these things are related this way, then the rates of change will be the same. So now we take the derivative of that equation with respect to t and relate these two variables. And because he's moving at all times, so both of these things are going to be functions of t. When you take the derivative, be careful to remember that fact. Left-hand side, of course, is simply dy dt. Right-hand side is the constant, 2/3, that doesn't matter, times the rate of change of y with respect to x. All right, so this is how we relate the two rates of change. The rate of change of how fast he's walking, the distance from him to the light, how fast he's walking, and how fast the length of his shadow is changing. Now we have taken the derivative, we can plug in all the numbers we know. That's just a recap from the problem statement. At the moment when he's 15 meters from the light, he's walking toward the light at 3 meters per second. If he maintains that speed, he'll reach the light in 5 seconds. So this tells us that x is equal to 15. That's the distance from him to the light. And the dx dt is approaching the light at -3. Plugging everything we know into that equation. So dy dt is equal to 2/3 dx dt, -3, and we get -2, right? And this means that the shadow length is shrinking at 2 meters per second. Okay, next time you approach a street light, you can see the same kind of situation going on. That the rate depends on the ratio between your height and how high the light is from the ground. And in this case, it's 2/3. There's the ratio between those two. But as you walk toward the light, the shadow behind you will also get smaller and shorter. If you walk away from the light, the opposite happens. The shadow in front of you will get longer and longer the farther you're away from the light. Any question? I have a question. What do we do with this? What do we do with that? Yes, if I want to know, that's right. If I want to know the length of the shadow, I would need to use that somehow. But if all I want to know is the rate of change of the length of that shadow, this is not going to change it at all, right? This doesn't show up in this equation at all. That's telling us that the shadow's rate of change is not dependent on how far he's from the light. Rather, it's only going to depend on the walking speed. So I'll write that down. Here, x does not influence dy dt. But if you want to know the actual length of his shadow, then that would be something you would need to know. Okay, so we found out how fast is the shadow changing. Now let's answer the second part of the question. How fast is the tip of his... What is going on with my microphone? How fast is the tip of his shadow moving at that instant? These are two different things. If you're watching this thing happen, the tip of his shadow is following him, but the length of this is changing. That is changing at the same time. Okay, so let's see how we can find that. And here's the tip of the shadow. And as he's moving toward the light, it's following him, right? It's following him, staying behind him. And there are two things changing how fast it's changing. It's affected by how fast he's moving toward the light, and also by how fast the shadow length is changing. Rather dx dt and dy dt. It's a combination of the two. Okay, when he moves, this triangle will kind of change shape. So it's this quantity right here. That's what we want. How far is the shadow from the base of the light? Well, that's represented by this quantity right here. And we know both of these things. This is given to us as -3. And that we found in the last part, -2. So that's -5 meters per second. So it's going at 5 meters per second toward the pole. Okay, if you're actually looking at the tip of his shadow, that's how fast it is actually moving. If you ignore the guy and all the other situation and just paying attention to that tip. Okay, any question on this part? You all look very, very tired. I know it's Friday. I know, and I stayed up all night watching the Cubs game last night too. But look at me. Yes, it was a great result. I'm very happy about that. But look at me. I'm up. Okay, we got another example to go over. Okay, this last one actually I divided into two parts because it's kind of lengthy. I think we can get through part A pretty easily. Part B, we'll see how much we can get done. If not, then it'll be like last time. I'll finish the solution before I upload the notes. Okay, here we got an inverted conical tank. So it's a cone upside down, right? The wide end is near the top, at the top. So this is what we got. And we're pouring water into this tank. At 0.011 cubic meters per minute at a pretty slow rate. The tank has a height of 6 meters. And the diameter at the top is 4 meters. So from here to here, it's 4 meters. Find the rate at which the water level is rising when the height of the water is 2 meters. So this is water that's already in the tank. As I pour water into here, this green part is going to grow. But it's going to grow all the way when it's exactly the same size. The level of water from the base to the surface, let's call that H. Okay, we'll call that H. And also note that the surface right here is a circle, right? Let's call that R. Okay, now you can see as water keeps being poured into this green part will grow. So H is going to get bigger as time goes on. R is going to get bigger as time goes on. It can only get as big as the tank itself, right? All right, so read the problem again. What do we want? Find the rate at which the water level is rising. The rate of the water level, H. At the particular instant when the water level is 2. When H is equal to 2. Okay, are we clear what's going on here? Yes? Okay. Okay, so notice what's going to happen here. As we pour more water, the volume of that green part will change. The volume of the water, the green part, it's also a cone, right? It's a smaller cone. So who knows the equation for the volume of a cone? One over 3 pi r squared h. Okay, good. Now that's the kind of equation that if this problem were to show up on the exam, we'll give it to you. Okay, we don't want this to be the reason why you can't solve the problem on the exam. So it's good if you know that, but if not, on the exam, you'll get that equation. That's the the volume of the water in the tank. If we pour in water, the volume of that green part is going to change. So that is the rate of change of the volume, dV dt, right? And how fast that volume is changing is how fast we're pouring the water in, 0.011 cubic meters per minute. And we want to relate that to dH dt, relating the rate of change of the volume of that green part to the height of that green cone, the height of the level. They're obviously related. The more water is, the higher the level. But precisely how is that related to this? Before we take the derivative, look at the right-hand side here. We got R and H. We can actually simplify this equation by a lot if we relate R and H. Look at the side, look at the cone, the tank from the side. We see a triangle, and the water is going to look like this inside the tank. If you look at just one half of this triangle, the height of the tank here, the big triangle, is 6 meters. The diameter at the top is 4, so the radius is 2. And for the smaller triangle, this is representing the height of the water. That's what we're calling H. And that's the radius of the surface of the water. That's what we're calling R. And just like in the last example, we have similar triangles again. We can relate the ratio of the sides of these two. Okay? So we see that 2 over 6 is equal to R over H. This means that R is equal to 1 over 3 times H. If I go back to this equation, now I can get rid of R altogether. I don't care about R, I care about H. I get rid of that R. I don't care about it at all, but I want H, right? So this gives me 1 over 27 pi H cubed. All right, and that's all we need. That's all we need to relate these two things. I know how V is related to H, right? So, take the derivative. And solving for dH dt. Going kind of quick here, but this is the pretty easy part. And now we plug in the numbers we're asked to plug in. We know the rate. And we want to know at the particular instant when H is equal to 2 squared. Sorry. Okay, and this turns out to be a pretty small number, 0.00, I'm rounding it a little bit, 788. All right, and I'll finish the part B of that example before I upload my notes. All right? Okay, that's it. Have a good weekend. Bring more energy on Monday, okay? See ya.